All right. We'll start the second lecture of chapter number 1. And today we're going to deal with vectors. And our learning goals for this lecture, the first is to identify the difference between scalar and vector quantities, recognize the properties of vector addition, demonstrate how to add, subtract vectors graphically, represent vectors by their components, demonstrate how to use components in calculation. So vectors and vector addition. So the first thing that we're going to look at is the difference between a scalar quantity and a vector quantity. A scalar quantity, it is only described by a single number, which is what we call a magnitude. So for example, we deal with time. And with time, you just say what time it is. Okay. Or you're going to deal with mass, usually in kilograms. You're not going to say in what direction. Or speed, and later on in chapter number 2, we talk about velocity and speed, and we will say the difference between these two. But when it comes to vector quantity, a vector quantity, no, it's specified by magnitude and direction. So for example, we'll deal with position. Your position, you have to tell me where. So we choose a point, a reference point. So for example, if we do an X and Y, so this point is 0, you have to tell me how far from this point and in which direction. And in that case, we're going to deal with a vector. Later on in chapter number 2, we'll talk about displacement, velocity, and we'll deal with these as vectors. So you're going to tell me east, west, north, south. So you have to identify a direction with the distance that's measured these. Okay. So that's basically what a vector is. So a vector is something that has a magnitude and direction. Okay. Now, how are we going to deal with writing vectors? So when we write things, if we write something and we put an arrow on the top of it, that's basically what a vector is for us. So we say now, this is basically a vector when we use this notation and we put an arrow on the top. Now, for easy, I just put that. Sometimes it's basically clearly stated as an error, but usually when we write this, I just basically use this way. It's a lot easier in writing. Now, in textbooks, now you're going to use, especially in the old days when they start basically printing things, now you're going to add this arrow at the top. So in books, they usually use bold letters, and these bold letters indicate that the quantity that you're using is a vector. So in many textbooks, when they actually use, let's say, a symbol for a quantity, let's say we're talking about force, and we use a symbol F. Now, when I write that, I will write an arrow on the top. That means I'm talking about a vector quantity. Now, in textbook, when they basically write it as bold, that means that's a vector quantity. When they write and bold, that means they're talking about the magnitude of this vector. Now, in this textbook, you may actually see the vector with an arrow on the top, which means it's a vector and it's bold, sometimes italic. In some books, maybe it's not italic. Okay. Now, the magnitude of the vector, usually we put the absolute value around it. Absolute value, that means I'm taking a positive quantity. So, for example, if you write 5, absolute value of 5 is equal to 5 minus 5. The absolute value of this is 5. It will always give you a positive quantity. So when we write A by itself, it's basically, I have this, for example, here it's A. A will equal to the absolute value of this vector A. And it's always greater than 0. And that's basically the magnitude. So in your textbook, if you see the symbol that we use for force or acceleration or velocity or whatever as not bolded, that means we're just talking about the magnitude of the vector. If it's bolded, that means we're talking about the vector of that, which means we have to state its magnitude and direction. And an example that we have here, we say the position of Abu Dhabi from Al Ain is 140 kilometers west. That's now a vector. But if I take the absolute value of that, it will be 140 kilometers, and I'm talking about the distance. So you have to distinguish. A distance is not a vector. I will say the distance between Al Ain and Abu Dhabi is 140 kilometers. But if I say the position or the location of Abu Dhabi from Al Ain, I will say 140 kilometers to the west. That's the distinction between what? Between a vector and a scalar quantity. So now you can change positions, and in this we'll take, let's say, position 1 here, which is the starting point, and we'll use position 2, which is the ending point. So you basically move between position 1 and position 2. Okay. This is what we're going to call displacement. And if I section this word for you, this and a place, you know what a place is. Now, placement, that means when you put things in. That's what the placement is. Displacement, that means if you change the place. And that's why you call it displacement here. You're moving from position 1 to position 2. So what is this displacement here? And here we're going to represent it by a vector. And this vector here, you can measure it, and it will have a magnitude. And you can also come here and you measure this angle here, and it will give you direction. So a vector always has a magnitude and direction. In this case, we chose displacement, which is a vector, and we can look at the magnitude and the direction. And the handwritten notation, it can be written this way. In the textbook, I told you it could be bold, and so on. So that's basically how we represent vectors. If we want to write, we always put an arrow, and the arrow here tells me that I'm moving from 1 to 2. And of course, I put the size of the arrow here. It may indicate what the magnitude of my vector. Let me look at 2 different or 4 different positions. I will move from position A to position B, and I have a displacement, and my vector here is A. I can move from another position, let's call it position 3, and I move to position 4, and I represent this with a vector A prime. But when I look at the magnitude of this vector, or the length or the distance, I will find that between 1 and 2 and between 3 and 4, they're equal in magnitude. And then I want to measure the angle here, and I can measure the angle here. And you can find that these two angles are also equal. So in that case, I will say that A prime is equal to A. So when the two vectors have equal magnitudes and directions, then we can say these two vectors are equal. Example, I can take my X and take my Y, and I can choose to move from here to here, and I can choose to move from here to here. Now, we all know that this is your first quadrant, this is second quadrant, this is third, and this is fourth. Your displacement is in the first quadrant here, but your displacement here in the third quadrant. Different locations. But this vector here, A, and this vector here, B, I can say that these two vectors are equal if they have the same magnitude and the same direction. So I don't want you to get confused that if the two vectors are equal, that means they have to be moving between the two same positions. No, they can be moving between different positions as long as they have the same magnitude, the same direction. The two vectors are equal in that sense. And that's why we say here the two vectors are equal when the absolute value of A and absolute value of A, that means the magnitude of A, equals the absolute value of B, which means the magnitude of B. When these two magnitudes are parallel, are equal, and when vector A and B are parallel, that means they are in the same direction. They make the same angle relative to, let's say, the positive x-axis. And in that sense, I will say the two vectors are equal. Now, the two vectors can have the same magnitude. That means I look at magnitude A and I look at magnitude B. The absolute value of A, the absolute value of B are equal. But these two vectors are not equal. And the reason is these two vectors are not parallel to one another. They're anti-parallel. The arrow is pointing this way, and the arrow here is pointing that way. They are in different direction, anti-parallel to each other. In that case, I cannot say vector A is equal to vector B. That's wrong. Okay. But I can say that A equals to B. Here, I'm just only talking about magnitudes. That's fine. Magnitude A and B are equal, but A and B are not equal because the direction is not the same. So that's basically how we look at vectors. So we represent vectors by an arrow, and the head of the arrow points in the direction of where we're moving. And the vector will have a magnitude and direction. Okay, that's basically how we are going to deal with this. Now, the point after that, you can basically have your X and Y, and you can move, and then from this you can make another movement. So that's a vector, that's a vector. How are you going to add these vectors together? You're going to look at a resultant vector. So how do we add vectors? Since we represent a vector by an arrow, so adding the vectors, when we add them, we're going to basically take the tail of the vector, which is the second vector that we're adding, to the head of the first vector. So for example, I have vector B here, and I have vector A here. Now, if I want to add vector B to A, that means I'm going to translate this, because this vector here and this vector here, they are equal. That's why we talked about this at the beginning. Why do we say that these vectors are equal? Because they have the same magnitude and they have the same direction. So this vector and this vector are the same. So in addition, I will always take the tail to the head. So when you put these two vectors together, now you're getting your resultant vector here, C, which is A plus B. Again, you do not write this C equal A plus B. You do not do that. Okay. What you do is you put a vector on top. That's okay now. That's basically how you add these vectors. Now, if you just want to write C, which is equal to A plus B, which meaning that that's wrong. That's why in the top here we say that the magnitude of C is not equal to the magnitude of A plus the magnitude of B. It may happen when the two vectors are parallel to each other. Okay. But in this case, it cannot be done. So usually what you do is you're going to add the tail, and that's what we're doing here, the tail of B to the head of A, and that's why we say C here is equal to A plus B. And this is your resultant vector. You can get the same resultant vector by adding A to B. You're putting the tail of B to the head of A, and in this case, we say it is B plus A. C here and C here is the same. But in this situation here, I cannot say A plus B. I will say B plus A. And in this situation here, I will say A plus B. I cannot say B plus A, even though you're ending up with the same result. But you have to be careful. So we represent the vector by an arrow, where the arrow, the length of the arrow will tell me the magnitude of the vector or relative magnitude of the vector to my drawings. And the arrow, the direction where it points is the direction of the vector. Now, in adding vectors, tail to head. Okay. Is this clear? Any questions on these? Now, in the case when you're adding two parallel vectors, yes, in this case, C is a displacement vector. Okay. Now, if you have two parallel vectors, A and B, and you want to add these vectors, we follow the rule. And the rule says is tail to head. So here you're adding C, which is equal to A plus B. Now, it happens in this particular situation, it's also safe to say that C is equal to A plus B, where C is the magnitude of vector C, and A is the magnitude of vector A, and B is the magnitude of vector B. But it's okay here to say that C is equal to A plus B. That's the only situation when the two vectors are parallel to one another, and when you add them, the magnitude will be like this. However, when they are anti-parallel to each other, and you want to add them, okay, then what you're going to do is basically you're going to add them this way. So that's your A and that's your B. That will be the resultant vector here of these two additions. So that's your C, but your magnitude here is not going to equal to A minus B. It's wrong to say that. Okay. So what we say that in this situation here, we have a negative sign here, and we put an absolute value. You never know. The magnitude of B might be greater than A. To make sure that the magnitude is always positive, that's why you put an absolute value here. So that's the only situation when they're parallel. You can basically, the magnitude will equal to the addition of the two magnitudes. But usually, in general, the magnitude is less. Okay. So now let's deal with the situation when we have more than one vector. And let's take three vectors. So we have vector A, vector B, vector C. So you see here that we're putting the head at the tail of vector B to the head of A, and then we're putting the tail of vector C to the head of B. That means I'm adding B to A, and then I'm adding C to B, which means I have A plus B plus C equals what? Equals R. That's the right notation for this situation here. Now, you can have different arrangements. So, for example, I am putting the tail of A to the head of B. That means I'm adding A to B. And then I'm putting the tail of C to the head of A. That means I'm adding C to A. Now, in this situation, it is B plus A plus C, which gives me R. Now, in both situations, you're getting the same resultant vector. But you have to be careful with which order you took. So, for example, if someone is trying to grade you and look at this, if you write for the first one here, B plus A plus C, they'll tell you this is wrong, even though you say, well, the final answer is right. Yes, the final answer is right, but that's not the right way for writing this. So you have to be careful with that. Now, we say here that vector addition is associative, meaning when I'm adding these vectors, I can add B to A, and I get a resultant vector here. Let's call it D. And then I will add C to D. And that probably, when I want to use my knowledge of trigonometry and add vectors, it may become helpful. Or I can add C to B, and then I will get an E, and then I will add E to A. And that's why here we have A plus B added to C, which gives me R, or I add B plus C to A, and I get R. So you can choose, okay, which vectors you want to add first, and then you add them to the third one, and that's why we say that this is associative here. This basically how we deal with vector additions. Now, when it comes to vector subtraction, it is similar to addition. The only thing that I'm going to do is, if I want to write A minus B, that means I'm adding B to A, but I'm going to invert B. That means I'm going to multiply it by a negative sign, which will invert this for me. Okay. So here I have A minus B. I have vector A, I have vector B, and I want to basically take the subtraction of that. Well, I will invert B first. And it's equal to minus B. And I'm going to add minus B to A. And you know the rules. You always take the tail to the head. And that's why you bring the tail here to the head of A. And what you have here now, you have basically A plus minus B, which is equal to A minus B. Now, the head of the vector here will point toward the second one. So you have to be careful with this notation here. And this is basically how you deal with subtraction of vectors. So here C is equal to A minus B. And here you can look at the magnitude of C is not going to equal to the magnitude of A minus the magnitude of B. This can happen only when the vectors are anti-parallel to each other, as we've seen in the previous slides. But in general, you have to take the magnitudes of this is not going to be right when we talk about the magnitude of vector C. Is this clear? Any questions so far on these rules? So we dealt with addition of vectors. We represent a vector by an arrow. The length of the arrow representative of the magnitude. The head of the arrow representative of the direction. In the addition of vectors, you always put the tail to the head and you add. And subtraction, we already dealt with it. It's like the case of addition, but you just basically invert the direction of your the vector that you want to subtract from it. Okay. So that's basically how you add and subtract vectors. Now, in any vector, you can also change this vector by multiplying by a scalar number. That means you can make the vector bigger, you can make it smaller, and you can also change its direction by multiplying by a negative. So for example, if you have your x-axis this way, and you have a vector here, if you multiply this vector by -1, you will get this vector here. Because you multiply x by a negative, x here is positive, x here will be negative. You multiply the y with negative, the y here is positive, the y here will be negative, and that will be basically the resultant vector. So you change the direction of the vector by multiplying by a minus, and this is when we talked about subtraction. You always multiply by a minus. But you can also increase your vector by any number you want. So for example, you multiply by 2 here and you get twice your original vector. You multiply here by -3 and you get 3 times the magnitude of your vector, but in the opposite direction. So that's basically dealing with vectors. You can multiply them by scalar to change direction or to change magnitude. And we already talked about how to add and subtract vectors. Is this clear? Any questions on these? Any questions on these? Okay. Now, when it comes to adding vectors, so how can we add these vectors? Well, let's take an example here. And the example here, a girl delivering newspapers covers her route by driving 3 kilometers west. And this is basically your direction here. This is east, west, north, and south. So she goes west 3 kilometers. Then 4 kilometers north, which is B here, and then 6 kilometers east. So you're adding tail to head, tail to head. So you're adding these 3 vectors. This will be your resultant vector here. And of course, you can measure the angle that it makes. Now they ask you here to how far is the resultant displacement, and they ask about the distance, total distance. Now, total distance is easy. You're just going to add 3 plus 4 plus 6, and that will give you 13. So she traveled 13 kilometers. But when she basically, how far is she from the initial position, then you have to find this resultant vector here. And you have to find the direction. Now, the graphical way, you have to do it by measurement. That means you have a graph paper here. And in this situation here, we're using every 2 squares as 1 kilometer. So what you do is you're basically putting here 6 squares. That means 3 kilometers. Then 8 here squares, which is 4 kilometers. Then 12 squares here, which is 6 kilometers. Now, for this one here, you really have to measure that. You take a ruler and you measure this. And then you multiply by that scale. And then you can figure out what? You can figure out the direction here, the angle. Okay. And this is now you're getting your resultant and the direction. But you do it graphically by measuring things. Now imagine if you have 5, 6, 7, 8 vectors, it will be time consuming to do that. But that's one way of adding vectors, and we say this addition here done graphically or by the graphical method. Now, there is another way that you can do that, and we can take another example later, but it's done using your knowledge of trigonometry. What I will do here, I will just refresh your memory and what you did in schools about Pythagoras' law. If you have a right angle triangle like this, where you have sides A, B, and C, and this angle here is a right angle, we always say that this is right angle triangle. Now, you know from schools that Pythagoras' law says that a squared plus b squared is equal to c squared. That's what you learned in school. And you also learned that the addition of all the 3 angles in a triangle should add up to 180 degrees. And if these angles equal 180 degrees, and this angle here is equal to 90 degrees, that means alpha plus beta is equal to 90 degrees. So if we apply this rule, Pythagoras, or later people want to prove this, if you go to this right angle triangle and you complete the square, that means if this side A, then you just complete the square and make it a square of side A. And the area here will equal to A squared. And you go to B and you complete the square, and the area will be B squared. And the area here, you complete the square, you will get C squared. Well, what has been found, that's A squared, the area of this square, plus the area of this square, which is B squared, it's equal to the area of C squared, and that's how we obtain this relation here for a right angle triangle, plus these rules that you have there. Now, this is Pythagoras' law. What is the relation between A, B, and C? Is there any relation between them? And the best way to do that is to take what's the ratio of A to C, so it is A over C. What's the ratio of B? It is to C, it's B over C. What is the ratio of A to B? It's A over B. Now, these were defined as sine related to the angle alpha here, for example, And they said sine alpha should equal to the opposite over the hypotenuse, which is equal to A over C. And this ratio here, which is the adjacent to alpha over hypotenuse C, which is equal to cosine alpha. And the ratio of A over B, it's basically taken as the tan of alpha, which is the opposite A and the adjacent B. So these are the rules that you learned before. You can do the same thing for alpha, by the way. But for alpha, for beta now the opposite is B. So sine beta is equal to B over C. Here you have B over C. So sine beta is equal to B over C. And cosine beta is equal to B over C, sine alpha. So you can see that cosine alpha and sine beta are complementary. And this is what you learn when you say that sine 60 is equal sine 60 is equal to cosine 30. And it's coming from here because these two angles have to add to 90 degrees. So you can either use alpha or beta. Now, if you want to just get A, for example, from the first one, you just multiply C with sine alpha. It will give you A. And you can do it from here, which is equal to sine C cosine beta as well. And you can do it for the tan. So these are the relations that you learn when you dealt with Pythagoras' law and right angle triangles. Finally, just to remind you of one identity that you have when you say sine alpha squared plus cosine alpha squared is equal to 1. Sine alpha is equal to A over C, which is A squared plus C squared. And cosine alpha is equal to B squared over C squared. So you're adding A squared plus B squared over C squared. And C squared plus B squared is equal to C squared. And C squared over C squared is equal to 1. And that's basically things that you learn. This is just to remind you of what you did in Pythagoras' law, which is right angle triangles. Now, what happens if you do not have right angle triangle? You can use the law of cosines. And the law of cosines tells you that C squared equal to A squared plus B squared, similar to what you have, minus 2AB cosine gamma, where gamma is the angle between A and B. So if you do not have a right angle triangle, you can always use this. By the way, in right angle triangle here, gamma is equal to 90 degrees, and 90 degrees is equal to cosine 90 degrees is equal to 0, and you get to C squared is equal to A squared plus B squared. So you can regard this as the general rule, and the special rule is when gamma is equal to 90 degrees, and when gamma is equal to 90 degrees, you get Pythagoras' law, which is for right angle triangle. And then there is another rule which we call the law of sines, where you take A, which is opposite to alpha, A over sine alpha equals to B over sine beta equals to C over sine gamma, and this is known as the law of sines. So in trigonometry, when you're dealing with triangles, you can basically rely on this to get these different sides and so on. Let's take an example here, which is similar to what we did when we look at the graphical way. Okay. And here we basically what you have here, a cross-country skier skis 1 kilometer north, then 2 kilometers east on a horizontal surface. How far and in what direction is she from the starting point? So now, when we look at this, she moves 1 kilometer north and then 2 kilometers east. And they want to ask you how far. Now, we can rely on the example that we did previously. We do this graphically. You need a graph paper, and you measure 1 kilometer, 2 kilometers, and then you measure this distance, and you can find this angle here or that angle, and you do that graphically. But you can do that with the knowledge of trigonometry. You don't have to measure things now. You don't have to take a ruler and protractor and do these things. What you have to do now is, you know that the magnitude of this vector here, using what we learned, that c squared is equal to a squared plus b squared. So c will equal square root of a squared plus b squared. So r here will equal to square root of 1 squared plus 2 squared, and this is basically the magnitude of your vector. Now you want to get the direction. Okay. So if you use your knowledge of trigonometry, you're going to look at inside your triangle and use either this angle or that angle. So since you started from here, you're going to use this angle here, phi, and tan phi will equal the opposite, which is 2, over the adjacent, which is 1, and that will give you an angle of 63.4 degrees. So now you can say that relative to this point here, starting point, you are at 2.24 meters away at an angle of 63.4 east of north, because this is your north, and you go east to measure this. By the way, you can measure this angle here. If this is 63.4, then this angle here will be 90 minus 63.4, which will give you 27.6 degrees. And you can also say that it's 2.24 kilometers at 27.6 north of east. But in this situation, we say it is east of north. Okay. And you also have that as well here. Sorry, 26.6. So that's basically how you can add vectors and get answers using your knowledge of trigonometry, or you can do it like what we did in the previous example, where you do that with graphical way. A graphical way is time consuming and you need to measure things. Trigonometry, it's you sketch things and you can use your knowledge of trigonometry and you can do that. Is this clear? Okay, any questions on this? Okay. Now, there's another third way, which basically is breaking vectors in terms of components. And then you can add the components, and we'll deal with that. So now, let's take a vector A here, which makes an angle theta with the positive x-axis. Now, this vector that I have here, I can, just like what we did before, I can say that I get to this point here by going that much in the x and that much in the y. So I can represent the y component here with ay and represent the x component here with ax. So I can say that my vector A here will equal to ax plus ay, and you're putting the arrow at the top of them, indicating that you're dealing with them as vectors. So now we can say that this vector here that makes an angle theta relative to the positive x-axis, it will have an x component and y component. So what is the relation here between the vector A, theta, and the ax and the ay? So I can say that my ax over a should equal to cosine theta, the adjacent over the hypotenuse. So now ax here will equal to a cosine theta. Similarly, I can say that ay over a equals sine theta. So the AY here will equal to A sine theta. These are how the X component and Y component related to the vector and the direction that the vector makes with the positive x-axis. So I can break the vector into components. But you have to be careful because you're measuring your angle relative to the positive x-axis. That means if now your vector is here, well, this is A, but you have to measure this angle here, theta. And this is what you're going to use here. And this angle here, when you do it this way, it will give you a negative x component and a positive y component. So now, when you have this vector, and you break the vectors in terms of components, if I give you the AX and I give you the AY, you can tell me what A is. A will equal to AX squared plus AY squared. And that will give me the magnitude of the vector. We're working backward. And if I ask you what the angle is, theta, you will tell me that tan theta will equal opposite over adjacent, which is the AY over the AX, where theta will equal to tan inverse of AY over AX, and this is what we call here calculated theta. Why do we do that? Because later on, you may add vectors together by adding the x components and the y components. And if I want to get the magnitude of the resultant vector, then I have to do it in that way. And if I want the direction of the vector, I have to do it in that way. Now, in this textbooks, things are always done relative to the positive x-axis. And we can use this rule for any vector, but we have to be careful. So now, when you are basically looking at vectors, let's take a vector here in the fourth quadrant. And this vector here that we have in the fourth quadrant, my AX is positive and my AY is negative. And if I use this rule here, it will give me the angle that it will give me. It may give me this angle here. It will give me minus 45. But what I want it relative to the positive x-axis. And that's why I have to add 360 degrees to the calculated angle if I am in the fourth quadrant. And I know that I am in the fourth quadrant if the x component is positive and the y component is negative. Similarly, if I am in the second quadrant, the angle that I will calculate is not going to be, because I will have a negative y component and a negative x component and a positive y component here. So the value is going to be negative, which is not right. So what I'm going to do is I'm going to add 180 degrees to the calculated value of theta to give it relative to the positive x-axis, if I'm using my definition here. How do I know that I'm in the second quadrant? Well, in the second quadrant, x is negative, y is positive. Now, if I'm in the third quadrant, my x is negative and my y is negative. That's when you do that, it will give you a value as if you are in the first quadrant, which is not right. To compensate for that, you have to add 180 degrees. So if you use the definition of theta equal to tan inverse of AY over AX, use that definition and put the AX as it is, either in the first, second, third, whatever it is. Keep the minus sign if there is a minus sign and for the AY, and the same thing for the AX. You will get a calculated value for theta. Now from these components, you will know if you are in the first quadrant, X and Y are positive. You don't do anything. If your X is negative and your Y is positive, you are in the second quadrant. Then add 180 degrees to your calculated value of theta. If your X component is negative and your Y component is negative, then you are in the third quadrant. The value that you calculate out of here, you add 180 degrees, because if you do it, it will give you a value as if you are in the first quadrant. And if your X is positive and your Y is negative, you are in the fourth quadrant, and in that situation, you will add 360 degrees. Is this clear? Is this clear? So you calculate your theta just based on your basic definition and put in the AY as it is. Negative, positive, put it as it is. AX, negative, positive, as it is. But then when you calculate it, you have to follow these rules. Now, when you are dealing with addition of vectors, remember we said when you're adding vectors, you always put the tail to the head. So now you have a vector A here, and you want to add to it vector B. So you're going to put the tail of B to the head of A. So you're adding these two vectors. And this is your resultant vector. Now, previously, you can do this graphically. That means you're going to use your measuring tools to do that. Or you can use your knowledge of trigonometry. And in this case, you're going to use the law of cosines. However, if you break the vector A into an X component and a Y component, and you come to this point here, and you measure this angle here, that vector B makes with the axis parallel to the x-axis, that means you also kind of break it into an X component and a Y component, you will find out that your resultant vector here, R, it has an X component where this X component is equal to the AX plus BX, and your Y component of Rx will equal to AY plus BY. So your resultant vector here, the X component is equal to Rx plus BX, and the Ry is equal to the AY plus BY. So now you don't have to add the vectors graphically. You don't have to use trigonometry to add these vectors, but you can basically start adding components. So you can add the X components together, and it will give you Rx. And you can add the Y components, and you get Ry. Now, if you have 5, 6, 7 vectors, algebraically will be much easier now. All you have to do is take a vector and break the vector into X and Y components, and go to the next vector and do that, and the third vector, and the fifth, and so on. And all you have to do is add all the X's together, and that will be your X component of the resultant vector, which is Rx. And you add all the Y components together, and that basically will be your Y component of the resultant vector. And then to get the magnitude of your resultant vector, it will be the square root of rx squared plus ry squared. And of course, whenever you do that, you can get plus or minus for square root, but we're taking a positive value. We need the magnitude, which is here absolute value. And then your angle theta, and here it's going to be calculated angle theta, will be the tan inverse of the ry over rx. And you know the rules. If you are in the first quadrant, you keep the angle as it is. If you are in the second quadrant, which means your ry is positive and your rx is negative, you add 180 degrees. If you are in the third quadrant, your ry is negative, your rx is negative, and you add 180 degrees. If you are in the fourth quadrant, your rx is positive, your ry is negative, you add 360 degrees. So you have another way of basically summing these vectors algebraically. You do not have to basically use the time-consuming graphical method or trigonometry where you have to break things in triangles and then basically start adding things. Now you can just basically rely on using this method. So what you have to do, as we said, the first thing that you're going to do is to identify your vectors, set up the problems. That means take an x and y components of individual vectors, then add the x's and the y's, and then calculate. And finally, you're going to look at your answer. Evaluate, is this the right answer? Any questions so far? Any questions so far? Good. Let's take an example to clarify this. And the example that we have here, a man has a map for a treasure. The following three displacements lead to the point in the field where the treasure is buried. If he starts from his home, from here, 72.4 meters at an angle 32 degrees east of north. So that's your north here. He goes east of north 32 degrees and he moves 72.4 meters. When he gets to this point here, he's going to move at 36 south of west. So that's your east, that's your west, and that's your north, and that's your south. So he's going to move south of north. So he moves at an angle of 36 degrees and he moves 57.3 meters. And when he gets to this point, he starts moving straight down south 17.8 meters. They tell you, give me the direction, the magnitude and direction. Well, you can do this graphically, and you can do this by using your knowledge of trigonometry, or you can do it by breaking each vector into components. So let's look at the first vector. The first vector has a magnitude of 72.4 meters. The angle here is 32. So relative to the positive x-axis, which we call it theta A here, it will be 90 minus 32, which will give you 58 degrees. So your x components will be A cosine theta A, which is 72.4 cosine 58, and it will give you 38.4 meters for the x component. For the y component, it will be A sine theta, and that will give you 61.4 meters. Now, when I come to the second vector basically makes an angle of 36 degrees south of west, but you want it relative to the positive x-axis. So you're going to add 180 degrees to it. And that will give you 216 degrees. And then you will take your x component as B cosine. So it is 57.3 cosine 216. And it gave you a negative value. It tells you that it knows. because of adding this 180 degrees, you know that you are in the third quadrant. And it gives you a negative value for your x component and a negative value for your y component. Now, when you come to the third vector, it makes an angle of 270 because you have 90 here, you add to it 180, so it's 270. The x component will be 0, and that's, you have no x component. And the y component, of course, will be what? Will be negative, and you get your y component. Now, all what you have to do is add all the x components together and add all the y components together, and you have here -8 for your x component, and you get 9.8 for your y components. Once you do that, you can figure out the magnitude of your vector, which is square root of rx squared plus ry squared. And when it comes to your angle, you use your definition, which is tan inverse of ry over rx. The ry is 9.9, the rx is -8, and it gives you -51 degrees. That's your calculated angle. But you know your x is negative, your y is positive. You are in the second quadrant, so you add 180 degrees to this, and you get 129 degrees. So if you go there, that's basically now your resultant vector. And this is the angle relative to the positive x-axis, which is 129 degrees. So you can see now that you can add vectors graphically, you can add the vectors using your knowledge of trigonometry, or you rely on the method of breaking each vector in components, but make sure you know where the vector is relative to the positive x-axis, and then add the x's and the y's, and then find the magnitude and find the angle. Is this clear? Is this clear? Any question on this? So you can deal with adding vectors in 3 different ways. I think the last one, it's a lot easier when we have the components. Okay. Well, we already said that the ax is equal to a cosine theta, and the ay is equal to a sine theta. That's all you have to do, where a is the magnitude of the vector. So now let's deal with this final. We'll deal maybe some of them in the next lecture, but let's do this one here. They give you these vectors where the tail of A is in the head of C, and then the head of B is coming to the head of A, and they ask you which of these relation would do that. Now, if you look at this, you will say, well, I have the tail of A on the head of C. That means I'm adding A to C, and that will be the resultant vector B here. So if you take B to the other side, it will be with a negative. So the right answer here will be A minus B plus C, which is C. Or you can use the rule where you choose a point and you come back to the same point. It will be 0 if you go in a circle. So let's take C, for example, here. And A is in the same direction, but B in the opposite direction. So you put it minus, and it's equal to 0. And that also the cycle that can bring you back or will give you this answer. So in today, basically, we just looked at a vector, and a vector is represented by an arrow, and the arrow, the length of it basically can give you the magnitude. The arrow or the head of the arrow gives you the direction. We talked about adding vectors graphically or using trigonometry. And then if you break a vector in terms of components, you can also add the vectors algebraically. Any questions on these?